Hello, I'm Burke Libby. I'm the primary developer. Ah. Hello, I'm Burke Libby. I'm the primary developer on the COVID Shield diagnosis server component. COVID Shield is a reference implementation of Google and Apple's exposure notification framework, consisting primarily of a mobile app and a server for it to communicate with. And I'm going to walk you through in this video a little bit of how to interact with the server codebase and a walkthrough of kind of the protocol that the mobile app and the server use to communicate. So first off, the application lives here at github.com/covidshield/server. There's also covidshield/mobile here. And first off, obviously there's a README. The development instructions are in contributing.md. So really the thing to know is if you're just getting started, you can run docker compose, presuming you have Docker. You can run docker compose up, and that'll launch MySQL and the two services that comprise the server. The two services are key retrieval and key submission. If you look at the specs for how this Google and Apple exposure notification framework works, it assumes the existence of a diagnosis server, and that diagnosis server has two responsibilities. One of them is to receive the uploaded keys from positive diagnoses, however you define positive diagnosis, and the other is to publish those keys to all users of the application. So those users receive these keys and feed it into what's called an exposure notification session on their mobile device, and then the mobile device generates warnings if it thinks they've been exposed to cases that have been, or to devices corresponding to users that have been diagnosed with COVID-19. So that is the submission and retrieval services, respectively. So if you want to actually run this outside of Docker, there's also guidelines here. The prerequisites are Go, Ruby, Bundler. Ruby and Bundler are used for integration testing, not for truly building the service. Protobuf, Protalk, Django, libsodium, and MySQL. Docker Compose is only required if you want to run this in Docker. So having those prerequisites already installed on my machine, I can run make, and that will build the key submission, key retrieval services, in addition to a monolith service. So that monolith is useful if you want the simplest deployment possible. We normally separate key submission and key retrieval because it's useful to be able to scale them differently. They have kind of different behavior in a production environment, because submission is fairly low throughput, but you definitely want it to be a little protected from abuse because it's dealing with encryption keys and things. Where key retrieval, everything it publishes is functionally public, but it gets hit quite frequently, so you want a good DDoS mitigation, caching, stuff like this in front of it. So we separate them, but monolith could be deployed in a low throughput environment and it would work just fine. So let's quickly dive into first. I think the useful thing to show would be the protocol. So this server listens on HTTP and for the most part uses Google protobufs as the communication of the protocol on that wire. So if I look at proto/covidshield.proto, this is the protobuf definition file for the whole project really. And the first thing you'll see is key claim request. Now, this isn't actually really the first thing, because the way we've assumed that this project would work is we think self-diagnosis is probably not the right strategy. If users are able to upload their keys as soon as they download the app, that means anybody on the internet can upload their keys without even having to download the app, just because of how the internet works. And we think that would probably lead to a whole lot of false positives and malicious use. So what we've designed is a scheme where we require integration from a healthcare provider in the region, or whatever authority is implementing this app for its people. So the way this is done is we have a really lightweight endpoint that health authorities can integrate with to generate a one-time code to send to a patient as they're communicating a positive test result to them, or however they feel like doing this. We really leave it up to people, but we have an example workflow built and an example kind of health authority portal application called Portal that integrates with this endpoint. So just to quickly pop up that, we have this deal here. We register a route at /new keyclaim with this new keyclaim function, and that is this. So we won't dive through the code too much here, but basically what happens here is the health authority posts a request to this new keyclaim endpoint with a token that they've been provided with, out of band or pre-negotiated somehow, and that returns back currently an 8-digit numeric code. The healthcare provider reads that code to the patient over the phone or however, and the patient then plugs that into their mobile app. The mobile app then sends this keyclaim request message to the server, and that contains the one-time code that they received and an app public key. So the app generates an encryption key pair and stores the private side locally and sends the public key with this request to the server. Then it gets back a keyclaim response containing, if everything went well, just a server public key. So the encryption scheme that's being set up here is, it's called a salt box. It uses some very high-grade elliptic curve cryptography, negotiates key parameters to be able to exchange encrypted messages after this, and be able to authenticate the client to the server additionally. So this is doing dual duty of encrypting it on the wire and also proving that the client is the client that successfully negotiated the one-time code with the server. So, okay, we submit this keyclaim request with a one-time code. We get back a response completing our pair of key pairs that we need to encrypt. And then the user's intention here is to upload their keys from the past up to 14 days, right? So the Google Apple Exposure Notification Framework allows them to extract keys from the framework upon whatever event the application decides corresponds to a positive diagnosis. So they do that, and then they fill them into this encrypted upload request. So what that entails is the server public key and the app public key, the encryption parameters that we just negotiated previously. Nonce is just 24 random bytes. It's just part of the crypto scheme. And then the payload is a serialized encrypted message. That message is this upload message, which just contains a timestamp to prevent sort of some kind of replay attack, and then temporary exposure keys is the keys defined by the exposure notification framework, just translated into a protobuf, and up to 14 of them. So this gets serialized and then encrypted and filled into this encrypted upload response and sent off to the server. The server then, looks up the corresponding key pair, validates that the client is allowed to upload the keys at this particular moment in time, decrypts the payload, and inserts the keys into the database. So that's kind of the upload side. The other side is the retrieve side. The retrieve side is partially pretty strongly defined by the Google and Apple framework now. We serve up a zip file containing two files, encoded.bin and encoded.sig, both of which are defined by protobuf definitions that we have copied from their documentation. So really it actually doesn't really matter what we're serving up here because we're passing it directly into the framework. Our server and our application doesn't actually do any dissection of those zip files. They're just handed into the framework. But in the interest of just walking through what they are, basically, it's just really just a bundle of keys with a bunch of cryptographic signatures proving that it was, in fact, our server that generated that zip file. And then a little bit of information about what timestamp range does this correspond to, what region did these keys come from. Region is a part of the kind of like app to server protocol as well. It seems to be meant for federation. So you could imagining especially like well, especially if we're implementing this province by province or state by state, you would certainly want states, especially in dense clusters of states like the northeastern US, you would want adjacent states to also come through in exports. Like Maryland, Virginia, DC, certainly you would want several states fetched by all of your clients. So this is what that region disambiguates. But it seems to me like the usage of this field is still kind of evolving within Google and Apple. So we return that and a bunch of signatures, and that's all fine. The thing that's a little bit different in our server compared to some other implementations is that we serve up the keys at predictable URLs rather than over some kind of like negotiated scheme. So these URLs, I'll show you, have this pattern. So if you hit the key retrieval service with /retrieve and then a region, which for Canada is 302, and then a period, which is a UTC hour number. So this is really just taking the current timestamp. Let's just show you. Time.now is the current timestamp. We divide that by 3600 to get an hour number, and then we round that to the nearest 6 times 6. So that's essentially the definition of the period. Now the reason for that is we can only feed 15 zip files into a client each day because this is just a limitation of the framework. And we also don't want to give away too much information about, we don't want to give away enough information to disambiguate the up to 14 keys that a single user uploads, right? So if you would imagine an adversary that had a big, Bluetooth dragnet or whatever, correlating these keys, it's better to serve them in larger batches so that it's far less plausible to associate multiple keys to the same person. And 6 hours is plenty to make that infeasible. And then authentication auth here is really it's like functionally impossible to actually truly authenticate an endpoint that a user has access to fetch as soon as they install an application. What we're trying to do here is just make it a little bit more resistant to casual abuse. This parameter is an HMAC using a key embedded into both the server and the mobile application of the region, the period, and the current timestamp, essentially. And then the server verifies that that all looks good before it proceeds to handling the request. And then, assuming everything went well, this just returns that zip file. Now, the one last thing I want to show you about this server is the database schema. So we have essentially two tables. There's probably another one getting added soon for some more abuse mitigation, but really what we're storing is diagnosis keys are the big domain object. This is like the keys that get uploaded by the application that we also return back to applications via the retrieve endpoint. And these four fields, key data, rolling start interval, rolling period, transmission risk level, are the definition of these keys in the framework. This is just the necessary data we have to store in order to satisfy the protocol. But we also store a region, which is kind of half part of it because it's really only part of the like server to client protocol, not part of the actual framework, but it is another necessary field. And then hour of submission is how we construct those retrieve buckets, right? So they show, every 6 hours of received keys. We actually store keys with timestamps on which they were received. But rather than storing the full timestamp, we round them to the beginning of the hour in which they were submitted, just to prevent being able to correlate keys to to prevent being able to correlate keys into groups of submission, even if the database is compromised. And then encryption keys is what gives a user permission to upload keys. So we've got these two key pairs, server private key, server public key, and app public key. We don't know the app private key because only the app knows that, but these are, 3 of the 4 keys of the key pairs. And the one-time code, which the genesis of all of this is that the healthcare provider posts to new key claim, and that generates a one-time code. And essentially what you get in this table is a record that only contains the one-time code. Then when the application goes through that key claim request, they null out the one-time code that corresponded to and start filling out these 3 fields. Remaining keys is used to allow the user to only upload 28 keys total over the course of their session. So a key expires after 14 days, but it also expires after 28 uploaded keys. Because when a healthcare provider gives you permission to upload, that gives you permission to upload your entire history of keys as the framework will give it to you at that moment, which could be anywhere from 0 to 14 keys. And then it gives you permission to upload keys each day after that for 13 or 14 more days. Now, because keys are valid for 24 hours, that means you'll get 1 more key every 24 hours, which means 14 and 14 is 28. And then created is used to determine when the key is 14 days old and therefore no longer valid. And region is just like above. This contains, 302. This is Canada. Could contain whatever other region. And that is essentially the server in a nutshell as far as the protocol and database schema go. So you'll note, we don't really hold any personally identifying information at all at any point. We don't receive it over the wire. We don't store it in the database. One thing that is coming down the pipe is we will be storing when a user posts an invalid code to that claim, to the key claim request endpoint. We will hold on to their IP address briefly until they submit a correct key, just in order to be able to mitigate the abuse of people guessing invalid keys until they find a right one. But that's the only situation in which there will be any personally identifying information stored, and it will be purged by the time we have their keys in the database. So I think that is the quick overview. One more thing to mention is unit tests, or integration tests really, are in the test directory. They're written in Ruby because it's just easier to write them that way. And I think that's it. So I hope that was useful. Definitely let us know if you have any questions or whatever, and yeah.